All right, everybody, we're going to move on a little bit and we're going to go to move on to Niels Bohr. Okay, you've talked about Dalton, we've looked at Thompson, and we looked at the Rutherford model. You guys did that in your notes. So I'm gonna help you through the next couple of scientists. Actually, Bohr, and then once you get to the next few scientists, it's actually a bunch of people, different gentlemen. So we'll start here just to recap a little bit here. When we talked about when Rutherford did his model, we kind of looked at the nucleus in the middle, and then you had the electron some distance away, but we really kind of don't know where that electron is. Okay, and the problem with the Rutherford model is that the electron is here, but you know because it's attracted to the protons in the nucleus, you know at the time, why wouldn't the electron actually spin around the nucleus and then end up going into the nucleus and spiraling in, really, and just crashing into the nucleus? And scientists knew as you did this, you would end up producing light, white light. But why would you not crash into the nucleus? So this question was long standing for a while. Now, Bohr did work with Rutherford, but the Bohr model is slightly different. So the Bohr model he proposed is something called the planetary model, or the idea of electrons being around the nucleus in these rings. So that was like the end result of this. Okay, and how did we actually do this is a little, not a little complicated, but it involves a little extra study. All right, so scientists at the time, what they would do is they would excite or add energy to certain materials, and they would produce these lines. They would not produce white light. When they added certain chemicals to flames, what they would do is they would sprinkle them into the flame, and they would take the light coming from this flame, and they would pass it through a little focusing beam here into a prism. Okay, and again, this is called a narrow slit, or a little opening, slight opening, just to focus it, and that would come through a prism. And when they shine the prism on a blank screen, they would see just individual lines, and they would see dark areas in between those lines, and they would not see a whole spectrum. So if you look at the bottom of the screen, you'll see there's various elements here. These are three different elements: hydrogen, helium, and I think mercury. And you'll see that you only see certain lines coming from these elements. Again, you would add energy to the element endothermically. The element would kick out these energies. Okay, so basically, what Bohr did was take the hydrogen atom, and only the hydrogen atom, and what he would do with that is he would calculate the energy of where these lines were in the spectrum. And he was able to come up with a mathematical calculation with this. And when he was able to do this, he was able to confirm through experiment and calculation where those electrons were in the hydrogen atom. And he believed he was able to find, an energy level, defined as an energy level around the nucleus, where those electrons were. All right. So again, going forward, so just a little background about how he was able to do this. Okay. It begs for a little understanding of what light and energy and electromagnetic radiation is. Okay, it's simply waves of energy, okay, that move through space at the speed of light. So there's all types of there's really electromagnetic spectrum. You've probably seen this in your other classes, and they move at the speed of light. Okay, so again, think of them as waves, like ocean waves. Okay, where you have a wavelength in these two different types of waves. All right, and some properties of waves, just like water waves is a pulse of energy. You throw a rock, into a puddle of water, and you get these waves of water that come out, or wind blows on the ocean and produces an impulse, and that's what these are. So a wave, some properties of some things how you can describe waves. Number one is something called a wavelength, and we use the Greek letter lambda for that. That's this upside down, almost like an upside down H. In this kind of font, it looks like that. And this is the length of a single wave. Now, you can take peak to peak, a peak to peak here, that's called a peak, or the bottom part is called a trough. So a peak to peak or trough to trough, but we'll say peak to peak, or even you can take mid to midline. However you want to do this, it's just the length of one wave, and then we're going to do this in meters. Okay? The frequency is how many waves will pass you per second. So say I was standing here, on the beach, and I was watching waves come at me. So I was like standing here, and I was standing here, and I was watching waves come at me. And if I was doing that, if waves were coming at me in this direction, Okay, how many waves would pass me in 1 second? So if I had a timer and I counted how many waves, you can see that in B or A, wave A would pass me because their wavelengths are smaller. So the smaller the wavelength, the more frequent the waves will pass you in a given amount of time. All right, so that's called a frequency. And again, frequency means how often will those waves pass you. More will pass you when the wavelength is smaller. Now, there's various ways we can measure this. We can measure it as waves per second. How many waves per second, right? We can do that. Sometimes they say, okay, 1 wave per second. Again, if something is a denominator, we could also call that seconds minus 1, or we can name it after a scientist whose name was Hertz. So we can call this Hertz, okay? So again, that's an H. Sorry, guys. We'll do it again. Hertz, okay? So waves per second, seconds minus 1, 1 over seconds, Hertz, all measure the same thing. That all measures frequency, okay, or little f. All right? So that's important to know. Now, interestingly enough, watch this. If you take the wavelength in, let's just say I take the wavelength in meters and I multiply it by the frequency. Well, let's look at our units. Our units are, the wavelength is meters, correct? And if we multiply that by over 1 over second, you guess that we get meters per second, which is equal to speed. All right? So if you multiply the wavelength times the frequency of any electromagnetic energy, you will always get the same number, and that number is C. That letter is C. Now, I don't mean big C, I mean little c. So again, big C was a specific heat of water. Little c is going to be this 3 times. So this becomes 3 times 10 to the 8 meters per second, and that is the speed of light. And the speed of light never changes. The speed of light is constant. So all electromagnetic energy will move at this speed, at the speed of light. Okay, so that's interesting to know. So just to review, there's 2 little things you got to know about waves. One is how long the wave is, and the other one is how many pass through per second. So, and when you multiply them, you simply get the speed of light. So if we had to figure out, if we had to take this and do this example, let's just say we know the wavelength of light in nanometers, and it's red light, and we know the wavelength, can we find the frequency, right? So if I know that lambda times f is the speed of light, okay, and I do know that, and I know c is 3 times 10 to the 8th, okay, meters per second, all right, I then can say, if I solve this equation for f and I isolate it, I can say f is going to be equal to c over lambda. So I can say 3 times 10 to the 8 meters per second, right? And I can divide that by the wavelength. Now, the problem with the wavelength here is that it needs to be in meters, and you're in nanometers, okay? So again, think about your scale, right? If we know the base unit is here, right? Here's your base unit. Nano is way over here to the minus 9th, right? To the 9. So if we are here, we're going to have to go that direction 9 decimal places to the left. So going 9 decimal places to the left is really multiplying by 10 to the minus 9th, right? So if I take this and I multiply this by 10 to the minus 9th, I'll now be in meters, and I can cross out meters. So I'm going to divide this by 690 times 10 to the minus 9th meters, okay? And I'm going to get a frequency, okay? So that you could figure that out, frequency, and you can multiply that and divide that together. If I do it here, okay, I'll simply get my number. You try to do this in your see if you get the same number. I'm going to go 3, okay, times 10 to the 8th. Okay, I'm going to divide that by 690, okay, to the minus 9th. Okay, and I'm going to get 4.34, okay, times 10 to the 14th hertz. Okay, and that will be my frequency. Okay. Now, it sounds like of course, it sounds like a big number, and that it is, because the wavelength is so small, right? It's a very small wavelength, so you're getting a lot of waves passing you per second. So that would be the frequency of red light. Now, what's the point of this? The point is that light has an energy to it, or light has numbers to it. Okay, it can be measured, and that's going to be important going forward. All right, so we're going to move a little bit. Okay, so if we move on to what the spectrum, now again, what does the spectrum really look like? Again, this is a quick a view of this. Okay, so you have this whole spectrum, and again, humans can only see this. We can only see visible light, which is broadened up here, and you can see we can only see 400 nanometers out to 700 nanometers. So this again would be your little prism. Okay, and again, if we put this down here, we can see these numbers here. Is that your short wavelengths would be here, and your longer wavelengths would be there. So red light actually has these much longer waves. And then as you get here down to violet light or blue light, you'd see this would be, more tighter waves. Okay. So again, once you get past this zone and this zone, we can't see any of this energy. So as you go from IR, which is the same as heat, okay, heat is energy we can't see, but that's past the red zone. Okay, so IR is infrared. Ultraviolet would be past the violet, so UV would be on this side. Again, higher energy rays are going to be in this direction where the wavelength is really tight. So you have like tight waves here, where you have very long waves here. Again, you have radio waves, your microwaves, things like that. Okay, so it's interesting to know like where you have. Now your energy is greater when you go in this direction. Okay, so you have high energy waves here, low energy waves here. Now, it's not important for you guys to know the entire electromagnetic spectrum, but you should know the relative energies. You should know that X-rays and gamma rays, these are gamma rays here, that's the gamma. X-rays and UV light is definitely more dangerous to you or higher energy than the lower energy, than heat or microwaves or lower energy waves are. Okay, so that's just an informational slide for you, right? Again, what does this really mean? Okay, we need to move forward. So what we do is we take this information, all right, and some crazy things happen along the way on this, and I'm going to go pretty quickly with this. Okay, at the time, a scientist, Max Planck, does some experiments and comes out with a bold statement and says that energy is absorbed or released in these small packets or chunks of energy. Okay, and he called these chunks of energy quanta. So if you ever heard of quantum physics or quantum energy or quantum leap, okay, that simply means little energy chunks. It's almost like going up the stairs. Like if you go up the stairs or down the stairs, you're changing your energy in these little steps or little chunks. Okay, Einstein comes into this thing and he says, okay, well, let's take these little chunks of energy, of light, and let's call these little particles or these discrete little particles, these little chunks of light, I'm going to call them photons. And photons are going to have specific energies associated with their wavelength and frequency. All right, and he comes up with this relationship between wavelength and frequency. So he says the energy of a photon, of this part of either whatever kind of light it's going to be, whatever color light it is, okay, is going to be related to, really has two equations, and both of them are related. The key is where that frequency and wavelength comes in. Okay, so he's going to say that energy is related to directly related to the frequency. So as the frequency goes up, the energy goes up. Higher frequencies, higher energies. Okay? So you're going to say high F, high E. Okay? So that's important to know. However, you can also relate this to the wavelength, and you can say that the wavelength down here, because it's in the denominator, as this number gets bigger, right, the energy gets smaller. So you can say high wavelength, low energy. Okay? So it's indirectly related to the wavelength, but directly related to the frequency. Energy is going to be in joules. That's going to be important. Okay, so your blue light, if you look down here at this picture, the blue light is going to have higher energy because the frequency is higher. The wavelength is smaller. Okay, that's important to know. Now, there's two numbers in here we haven't mentioned. Again, c is going to be the speed of light. Okay, so that's going to be so you're going to know that number. All right, and h is a special constant that Max Planck developed and discovered within this relationship. And this is a tiny number. It's 6.63 times 10 to the minus 34 joule seconds. Now, again, you read that right, minus 34. So it's a very small number. Okay, so to repeat, you will always have H and you will always have C. So the only thing you really have to worry about here is E, the wavelength, and the frequency. So that's going to be a big deal. So that's what you're going to have to be able to be concerned with. We're not going to do a lot of calculation. We're going to do a little calculation with this, but we're not going to do a lot of calculation with this. So we'll do a quick energy calculation down here. So this says, what is the energy in joules of a single photon of red light with a wavelength of 690? Okay, so looking for the energy. Now, because they're giving you the wavelength, which is lambda, we're going to use this equation. So we can call this equation number 1. We'll call this equation number 2. We're going to use equation number 2. So we're going to say E equals H times C over lambda. Okay, so that's kind of easy because we know H is 6.63 times 10 to the minus 34 joule seconds. We're going to multiply that by 3 times 10 to the 8th meters per second. Okay, and we're going to put that over the wavelength. And again, the wavelength has to be in meters. So we're going to do the same thing that we did before. We're going to take 690 nanometers, and we're going to multiply it by 10 to the minus 9th, and then we will get 690 times 10 to the minus 9th meters. Okay, and we're going to put this together. All right, and we will calculate this really quickly. Grab your calculators and let's calculate. We'll take 6.63 to the minus 34. Okay, we're going to times that by 3 times 10 to the 8th. Okay, and we'll divide that by 690 to the minus 9th. Okay, and I'm going to get 2.88 times 10 to the minus 19th joules. Now you're going to look at this and say, well, whoa, and look at your units too. You're going to love this dimensional analysis, people. Seconds cancels with seconds. Okay, meters cancel with meters, and you're left in joules, and that's why this works. Okay, so you might look at that and go, wow, that's a little joules, right? That's a really small number. Well, again, this is a single photon. This is a single blip of red light, which has that energy. All right, so again, light has energy. Okay, and that's important to know. Your blue light, your violet light has high energy. Your red light has low energy. Okay, so that's important to know that these energies can be calculated, and that's an important part of this. All right, so what is Bohr's model? So using this information, let's just go over Bohr's model really quickly. All right, so Bohr's model, again, now is going to say that we start with electrons start in something called the ground state. So around the atom, you have the nucleus. You have the nucleus in the center, and then you have electrons going around the nucleus in their lowest possible energy states. So they're going to be as close to the nucleus as possible, but in these energy levels. Okay, and what's going to happen is if you give those atoms energy and you put energy into the system, again, and that's going to be your endo step, right? If you put energy into the system, that's an endothermic step. So we're going to go endo here. That electron is going to be absorbed by the atom. Okay, and what that's going to do is pull that electron further from the nucleus in something called the excited state. All right. So, and again, the higher energy level, which is really higher the potential energy level. Again, we've done this when we did the energy. So energy in, the potential energy of the electron rises, goes away from the atom. Okay, and it kind of gets stuck there for a brief moment of time, and then it falls back down. You can see it fall. It goes back down to where it was before. Okay, and what's going to happen is once it does that, light will come out, and that will be exo. So energy in, the electron goes up to a higher energy level, then the electron comes back down, and the light comes out. So as long as you're shining energy in, energy is going to come back out of the atom. Okay, now depending on the energy jump is the color of the light that you get. All right, so let's just see this is the spectrum of the hydrogen atom. Okay, now where does that come from? What happens is you'll have energies that electrons on certain energies will jump to a higher energy level, and then will fall back down. And when it falls back down, it produces light, and that is that beam of light you see. Maybe an electron was here, and it gets pumped up to this energy level, okay, and then it falls back down a higher energy, and it'll become a beam of green light. Okay, maybe an electron is there, and it jumps up to a higher energy level, and comes back down and produces blue light. Maybe an electron is there, and it pumps up to a higher energy level here, hangs out there, and falls back. Okay, so electrons can kind of bounce around here. As long as you're putting energy in, you're going away from the nucleus. Now, your energy levels will be marked 1, 2, 3, 4, 5, 6 going out from the nucleus. The nucleus is in the center. Really, 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 really important. Energy increases the further you get from the nucleus. Okay, let me repeat that. Energy level 6 has higher energy level than 5, which is higher energy level than 4. So this is high E out here and low E in here. Okay, really important you don't mess that up. Okay, so that becomes the bright line spectrum. Okay, every atom has its own spectrum. Really important. Colors only appear in certain areas because the energy of the photon depends on the difference in the energy level. The bigger the jump, the more towards the violet end you'll be. Okay, so longer jumps, closer to violet. The shorter the jump, the closest you are to red. All right, now every element has a different setup of electrons. And so because of that, you're going to have different colors in the spectrum. You're going to have different bright line spectrums. Now, you may notice that elements cannot exist here. They cannot exist here. They cannot exist in between these levels. They can only be on that level, okay, on one level or on other levels. Okay, just like a staircase, right? If you had a staircase and you're going up the stairs, you can only be on a step or on another step. You could skip steps, and when you come down, you could skip steps, but you can't be right there, right? You can't be in between steps. So that's an important thing to know, all right? So the color is dependent on the total jump of the electron as it goes back to the nucleus. And think about this. The electron is here, that's going back to the nucleus or back to a lower energy level and has different options. An attraction is being formed to the nucleus. Attraction is formed, energy is released. That's why it's exo. Okay, so that's the key. Now, one last thing, really important. All right, the colors are only produced on the return trip when electrons go back. All right, so let's just review this whole thing. This becomes Bohr's model with an electron in the middle, a nucleus in the middle. Everything else going around it in these energy levels, and that's why the electron doesn't fall into the nucleus because it has an energy value it's stuck on. Right? So summary of the Bohr model. Okay, electrons are going to be held in something called orbits. Okay, so this ended up being something like the planetary model. All right, so you have this here, and you have this orbits around the nucleus. Okay, now electrons are going to be able to jump to higher energy levels. So if I did my little atom here, you can jump from this energy level out to a higher energy level when you absorb energy. Okay. And that becomes the excited state. So the excited state would be out here. Okay? You're always starting from a ground state. All right? Electrons don't stay up there for long. They fall back down to lower energy. So this electron will fall back to various energies below it. Okay? And when they do that, they're going to emit energy as light. Okay? Again, so this is the this is the endo version. This would be the exo version. Right? You can emit this energy as light. So in the past unit, we emitted energy as heat. Here, we're going to emit it as light. Okay, so important to know that the energy is light. Okay, so you see an idea here of what's happening. Electrons can go up in this direction. They can go up to certain steps, but when they come down, they emit the light. Okay. Electrons cannot rest between the levels. They can only be on a level. They can't in between. That's right. That's why also you can't step between stairs, right? You can't step between rungs of a ladder. If you have a ladder, right, and you have the rungs on a ladder, you can't be there. You cannot be in that spot, right? So if I go back, so lastly, the spectrum that you see, okay, the spectrum that you see, again, if you take this light and you shine this light on a screen, you will see these bright lines being seen on this. And again, we'll see this a little in class when we do our lab. Okay, hydrogen only has these 4 lines. Okay, so this would be the model of the hydrogen atom. However, Bohr's model only worked for hydrogen. So again, sounds like a great idea, and he was able to explain these things, but the problem is at the end, it only worked for hydrogen. So it was a good start. So the bright line spectrum element shows unique lines produced from energy jumps. Again, unique. Every element has its own bright line spectrum. And like these days, what do we use that for? Well, a good idea is to identify elements that way. It almost acts like a fingerprint. Making mistakes. Sorry, guys. This would act. Sorry. This would almost be a fingerprint. So think of it as a fingerprint. All right, fingerprints are unique to all people. Each element has its own setup of lines, which we'll be able to see in school. All right, when we come to class to see the labs. All right, so I'm going to stop here for the Bohr model. Make sure you review this, go back over it. You definitely need to explain it. There's a lot of questions on ground state, excited state. Okay, ground state would be closest to the nucleus. The excited state is this temporary distance away. All right, good luck with everything. Talk to you soon.